Active 3D sensors send structured illumination to the scene to achieve robust depth estimation. They are now widely deployed in many real-world applications. However, one limitation of active 3D sensors is their maximum sensing distance. One naive way to increase distance is to use a high-power laser, which is challenging for mobile or wearable devices. Furthermore, it also increases the eye safety distance, which is not ideal for consumer devices. In other words, the goals of achieving lower power consumption, longer sensible distance, and shorter eye safety distance often contradict each other. Our key observation is that for many applications, we only need to estimate the depths within a region of interest. For example, in AR applications, we only need the depths around the virtual object. It is also important to note that depths on the textured regions can be estimated even from passive image sensors. We only need to project light to textureless objects. Furthermore, when the camera motion is tracked, which is common for AR/VR applications, we only need to project light to regions where the depth estimates have high uncertainty. Based on these three observations, we propose an adaptive 3D sensor, which consists of a stereo pair of cameras and a projector. The projector only projects light to a small region of interest. Since the optical power is redistributed and concentrated to this region, high signal-to-noise ratios can be achieved. We propose a framework to theoretically analyze the benefits of our method as compared to off-the-shelf full-pattern sensors and state-of-the-art line scanning sensors. To achieve the same maximum distance, our approach consumes the least power while being the most eye-safe. Please see the paper for detailed derivations. Existing LCD or DLP projectors are not capable of concentrating optical power to a small region of interest. We propose two hardware implementations to achieve the proposed adaptive illumination. The first one is based on a phase-only spatial light modulator, which can project light to arbitrarily shaped regions of interest. Our second implementation combines a 2D MEMS mirror and a DOE dot pattern generator. By rotating the MEMS mirror, the laser hits the DOE at different angles, such that the dot pattern is directed to different regions. We compare our adaptive approach against existing 3D sensing techniques by emulating all approaches on a single phase-only spatial light modulator. We validate the performance of our method in real-world experiments. Here the scene is illuminated with 4 kilolux of ambient lighting. Notice the adaptive dots are more visible due to having higher SNR than line scanning and full-frame sensors. As a result, we get higher quality active stereo performance. Here we show comparisons against passive stereo and a long-range experiment under 50 kilolux direct sunlight. Despite the extremely strong ambient lighting from the sun, our sensor still performs well. The adaptive pattern can be generated in real time by computing the SLM phase map on a GPU. Please see our code for a CUDA implementation. This video shows real-time demos. Notice the depth quality increase when the laser is turned on and the moving objects are adaptively illuminated. In summary, we propose adaptive 3D sensing and demonstrate its advantage in a theoretical framework that jointly considers range, power, and eye safety. We implement the proposed adaptive active stereo approach with 2 hardware prototypes based on SLM and MEMS DOE. Real-world experimental results validate that our sensor can adapt to the scene and outperform existing sensing strategies. We hope the proposed method can enable the use of active 3D sensing on power-constrained devices such as augmented reality glasses. Check out our project website and code for more information.